Hello everyone, good afternoon, good evening. Welcome to another ATA EV group meeting. Got lots of news to get through on the global scene, and then we've got some local stuff, and then we've got some an interesting talk to follow. So just to start off with some news around the world. At the moment, the EV sales in the UK for the summer quarter this year are almost they're almost double compared to the previous quarter, with 5,000 EVs being registered. And I don't know whether you know, but in the UK you can get a grant of £5,000 if you buy an EV car, and if you buy an EV van, that's an £8,000 grant. So that sounds like a good thing. A car and money. Fantastic. What you need is a gold watch, and you could become a rapper. Also, Norway's EV sales make up more than 14% of total car sales there now, and sales of the plug-in hybrid BYD Kin in China are getting stronger every month, with 1,700 sold in September, which is 400 up on last month. So that's still less than 0.1% of the car market in China, but the trends are heading in the right direction there. Also, Mercedes B-Class EV goes on sale in Europe officially on November the 3rd. And the Kia Soul EV has had its range tested by a journalist for Inside EVs, and it achieved a range of more than 160 kilometres. So that's pretty impressive. Also, the Visio M, a small all-electric vehicle produced by a German company, TUM, is soon to be has been shown off in October. It has some pretty impressive specs, as a 160 kilometre range, only a 15 kilowatt motor, but it does 120 kilometre-hour top speed, carries 2 people and luggage, constructed of carbon, plastic and aluminium, with polycarbonate windows. So it's like a weight-saving move there, going to polycarbonate for the windows. The car weighs 450 kilos, and the battery itself is 85 kilos. Also has some intelligent passenger safety systems with radar and cameras and all sorts of trickery that set off airbags before a collision occurs. So hopefully that works well. Otherwise, there'll definitely be a collision if those airbags set off just prematurely. There's also Tesla taxis now in Holland. So if you're out in Holland, forget about pedaling home on your bike. Get a taxi and burn some rubber electrically. Also, the Chevy Bolt, the 216 model Chevy Bolt, will be coming out with a more powerful and efficient design, and it's using less rare earth magnets. It's also getting a slightly larger petrol range extender engine, and the car's going to be slightly lighter, I think by 15 kilos. So probably means they're changing the spare tyre over to one of those little emergency ones or something. But yeah, that's right. Yeah, it could be a little bit more petrol than electric. Well, it's only 50k range, so it's getting there, but far from it. Now, good news. There's over 600,000 road-registered EV cars that have been bought globally so far. I think that's worth a round of applause. All those people have. Has anyone here bought an EV in the last 5 years? Excellent. That's very good. For the rest of you, shame. Rest of me, shame. I brought mine here. Oh, fantastic. Those who have made theirs, of course, Mario, well done. And also, according to CoverHound Insurance, EVs are on average $200 cheaper to insure compared to ICEs. So, yay on that front.
Rego, you get $100 off too.
Oh, I get $100 off on your Rego here in Victoria.
Yeah, but make sure you say it's a hybrid.
Oh, you're going to say it's a hybrid. Okay, for all those out there in Google Plus and YouTube land, make sure you claim your $100 discount on your registration of your hybrid all-electric car. For fans of two wheels, the KTM Freeride E has officially been launched, and it looks like quite a fun little vehicle. The battery's quite light. It'll do about an hour of fun free riding before you need to charge it up, but it will charge up completely full in 80 minutes from completely empty. So that's pretty good. Also some news for the ATA. For those that don't know, the ATA has received a $250,000 grant from the Google people to bring solar power to East Timor. So they've got a solar power project that's running in East Timor, and that's $250,000 going towards that. And I think that's we could certainly helping make a new country more sustainable. And if only things could move that quickly here in good old Oz. Also, some local news on the EV front is that last weekend the AEVA had their annual general meeting, plus they had their Go Electric Sustainable Festival. And for those that that didn't go, we had our famous battery guru Paul Patton, who spoke on the Saturday, and then on the Sunday the ATA had a stall there, and it was a chance to go and have a look at the Tesla. Also a beautiful little Renault single-seater vehicle that was a lovely little concept car. Plus there was some nefarious e-bike companies there, of which they won't be named for fear of conflict of interest. And overall, it was a good day. I'd just like to thank the AEVA and also Bryce Gatton and also Paul Patton for speaking there, but especially at AEVA in general, and Bryce Gatton, who is also a member of this group, for being integral in the organising of that. And there were some really nice vehicles there to see. So, and that was held at Coburg Town Hall. So very good. And I think that the residents of Pentridge prison apartment block probably heard an occasional whirring as some electric bikes and other vehicles use that as their test ride area. Luckily, it wasn't little two-strokes buzzing up and down there. Some other things to mention is that but basically there's so many good things going on the EV front that I think that we're going to see what we can do to add that to that mix. One of the things that was brought to my attention is that Ralph Feasing, who's the president of the ATA, was bigging us all up for our wonderful previous efforts on EV expos, and he would love to see another one happen next year and keep them happening yearly. I know for myself that time is a precious commodity now that I have more adult responsibilities. So what we're looking for is expressions of interest of general members to get involved in the organising committee for an EV Expo to be held next year. I'd probably suggest later than February, which is the time that we held it this year, just so that we've got more time to organise. But I think it's a really good event, and if we can get some interest, I'd like to call for an EV Expo committee meeting to be held next Wednesday here at Swinburne. So I'll be getting on the phone and emailing and seeing if we can drag up some interested people to be involved. If we get a whole lot of people involved, then we all have to do just a little bit, rather than just leaving it to a few people. We end up getting a little bit burnt out and feel maybe a little bit daunted. But if we all pitch in and we all put a little bit in, we all take a little area, a small area of responsibility, then I think that we can make the expo happen, and not only happen, but make it better than it was in the previous 2 years. I think it's something that could grow, and who knows, one day we might even hold it in Jeff's shed. That would be amazing. There's some other things also that we've got we've got an AGM that needs to be held for this highly esteemed group. So next month's meeting will be our AGM. So all positions will be up for nomination. So if you want to get involved, there's your chance to become part of the committee. If you can also be nominated for a general committee position, so that we just get as many bods as possible in to help become part of the inner circle to help organise things, to set the agendas for meetings, to look after the general business of the EV, and to help set direction generally. So I think it's something worthwhile doing. I'd like to see some of the regular faces here who haven't taken up committee positions to be able to step up and get more involved. It's not, we're not asking huge amounts of time, but we do need people who are committed and prepared to do a little bit every month, just to help this group grow and to help push the EV movement forward. So let's see, was there anything else I needed to mention? Yes. Also, for all those that are out there on Google+, hello, is there anyone on Google+? Wave to me if you're on Google+. Yes, I can see a couple of you. Right, if you're on Google+, you can post questions for this session now. You can do that online. If you you can find their post questions on the event site, on the event page. Well, not only that, but you can also post questions prior to the event. If you're having trouble finding us, go to the ATA site, find us, find the event. It'll bring you the link to our Google Plus page, and there you can post questions prior to the event. So if you're not going to be here, or you're too drunk to get into your car and you're sitting at home with a few cans in your hand, that's all right. You can post your questions, and hopefully we can have them answered in your absence. And I'll just check with Adrian. Is there anything else I needed to mention on the tech side of things?
What's the new four-wheel drive car?
Model
S four-wheel drive.
The Model S. Yes, the Model S is out, and for all those that had a chance to see it on Sunday.
No, the four-wheel drive version of the Model S.
Oh, the four-wheel drive. The Model D.
It's got an E85D.
Oh, okay. Oh, there we go. I've just been told Tesla's dual motor four-wheel drive is being launched out and about. So if anyone's got a spare 150 grand or whatever it costs,
120 US, I don't know.
120 US, chicken feet. If you can make sure that you buy it and drive it to the next meeting. If you do drive a Tesla, the new Tesla to next month's meeting, I guarantee you'll get a position on the committee. Guarantee it.
0 to 100 is 3.2 seconds, they're claiming.
0 to 103.2 seconds. Yeah, that's pretty good.
They claim it's about the same as McLaren F1. So.
The same as McLaren F1?
Yeah.
Wow, that's pretty amazing. You certainly get here quick, except for traffic.
It's just under 700 horsepower.
We already have a question.
Oh, we have a question. Hey, thank you, Google Plus people. Love you guys and women. Thank you very much.
Rebecca asks, are we going to have a Christmas event this year?
Are we going to have a Christmas event? Yes, why not, of course. We should have a Christmas event. And I nominate Rebecca Lee to organise that one. Thank you, Rebecca. Love ya. and get the wheels in motion for that and have an announcement at next month's meeting. Thank you very much. Now it's time to bring up our highly esteemed mob of Swinburne students, all looking like they're bouncers or some such in their black uniforms, roadies or bouncers. Now, we've got Andrew Johnson of the Swinburne SAE team. He's the chief engineer. He'll be giving us a rundown on the team's 2014 race program, and we'll introduce the rest of the team. So if we can have a little round of applause for Andrew Johnson.
Thank you. So my name's Andrew, chief engineer, and I'll be giving you guys a rundown of our 2014 car. On the slide here behind me, we have our powertrain package for this year. We're running 2 axial flux permanent magnet motors, brushless DC, and we had a look into various transmission systems at the start of the year. Our previous vehicles all used some kind of reduction system between the motor and the rear wheels, and from a number of tests and calculations, we've actually managed to reduce weight by going to a direct drive system. These motors are incredibly torquey, as most all electric motors are, and that has allowed us to move forward with this direct drive platform.
Can I ask a question?
Sure.
You've got them inboard mounted. Did you go through the pros and cons of hub sort of motors, the wheel basically bolted to the motor?
It's not something that we considered with these particular motors. Due to the size of them, they are quite large. They don't actually fit into our wheels. Also, packaging our suspension points might be a little bit difficult, and also the increased unsprung mass. These motors are 12.5 kilos. While they're incredibly light for how powerful they are, they're still a little bit too heavy to stick inside a wheel onto the unsprung mass. So we have decided to keep them inboard mounted.
Does it really make a difference on a racetrack, which is pretty smooth?
It
on
does.
a rough road, I can imagine.
It does make a difference. By moving that weight onto the unsprung mass, it means it would have greater forces through our suspension components. So then we would have to increase the mass and strength of all our suspension components in order to handle that added force. So in order to keep things light, we've kept the motors with the sprung mass, and it's reduced the forces to our suspension components. So our goals for powertrain were to reduce weight from the previous vehicle and also increase the reliability. So by removing the transmission system, we've been able to reduce the amount of components that we have, which has increased the reliability. Are you supposed to be talking about this? Yes. Yeah, I figured so. Sorry, I've got a bit ahead of myself. So I'd like to invite down our powertrain team to talk about powertrain this year. So I have with me the section leader of powertrain, Brad Gallop, and Tamby and Ian, who have helped out with the section.
Hi everyone. I'll sort of move on from what Andrew was talking about with powertrain. So going on from the goals, obviously with reduced components of no transmission system, we've lowered cost, and there's less joints in the parts, which means there's less manufacturing errors possible. So with the 2 motors, we've also isolated each side, so they're not connected in any way. So any error on the right-hand side, for example, won't carry over to the left-hand side. So just going on from the motors, so these are 2 permanent magnet DC motors. So we used these last year, and we've chosen to use them again. They're rated to max 100 kilowatts and 50 kilowatts continuous. They can run up to about 4,000 RPM, but we are not planning going anywhere near that because of the 1-to-1 ratio. So if we did, we'd be going about 300 kilometers an hour, which I'm not planning on doing. So these require cooling through the core via water cooling. So we basically run 2 loops through both motor controller and the motor. That's isolated between the left and right hand side. And the outer casing, which you can see on the screen, the black part, needs air cooling, which we basically run a scoop through the body to get air to the motor. So this is just a cross section of basically one side of what the powertrain system is. So just to sort of reiterate, the powertrain system this year is, our job is basically to get the power from the motors to the wheel hubs. So Scott and Will talk more about the electrical side. But so because we have a reduced amount of components, it means it's lighter, it's more compact, so it fits within our constraints of the smaller chassis this year. And this also means greater efficiency. So overall, we've got about 76%. So this is accommodating powertrain efficiency, wheels and tyres, corner assembly, and the electrical side.
Last year you had some CV joint issues. Did
Yep.
you redesign your CV joints this year?
So what I'll get those guys who will talk more about it. So with the 1-to-1 also, it was a bit of a, weren't too sure about it at the start of the year whether it worked, but we've done a lot of testing to basically confirm that it's going to work for application. So we did a lot of dyno testing to basically simulate the tractive effort that it puts out, so basically the force that the wheel puts the power to the ground. We also used last year's vehicle to simulate a 1-to-1 reduction, so we actually changed the sprockets on the car last year as it had a chain and sprocket system. And we did a lot of simulation through calculations to basically back up our theories. So what we're looking for, we wanted to confirm that the vehicle would make the endurance event, and we wanted to make sure the performance was to our requirements. So with the aid of this year, we've got smaller wheels, which the dynamics section will talk about, reduced drag, which aerodynamics will talk about, the increased efficiency, and yeah, with all that together, basically it makes our 1-to-1 drive system plausible for our competition. So I'll now hand over to Tanvir, who will talk about our CV joint system.
So this year our primary target for the CV joints was that we're looking into reliability, efficiency, and lightweight component. So first we looked into a couple of standard products that are manufactured by different manufacturers already. As you can see, there's a picture of TKN Rosetta style joint and a picture of a tripod joint, which is widely used by FSAE race teams all over the world. These components are quite pricey, and to the level we wanted the specifications, we did a simple calculation on their specification and based on their cost as well, and we found that if we manufacture our own tripod housings, it would be most cost-effective way and will serve our purpose best as well. So what we needed for this year for our tripod joints, as you already know, is a well-known fact for tripod joints are that their failure mode is if there is any discrepancy of the length of inboard and outboard housings, the tripod will pop out of the housing system, and it causes a major damage to the car components, and this will destroy usually the corner assemblies as well along with that. So when we did our calculation, we found that we need around 10 millimeter of plunging length for each housings, and therefore we required to manufacture housing that will include the new length of inserts which will have that at least 10 millimeter plunging area. Also, the transmission angle, as you know, when the suspension travels on the bump and droop, it will change the transmission angle, and based on our calculation, we record up to 10 degrees of transmission angle. Also, there are a few other specifications that you can see. We want our assembly to be sub 500 grams, easy mounting options, and can operate up to 4,000 RPM as per record, which our motor can take theoretically up to. So when we looked into the products off the shelf, the Taylor race had 8 degrees of transmission angle, which obviously not suitable for us, 6 millimeter of safe plunging length, which is way less than what we needed. Also, the assembly weight is just over our targeted weight. Whereas GKN had a acceptable, well, really good transmission angle. However, the assembly weight is huge, almost double. That's why we dropped off the GKN VL joint system. So I'll pass on to Ian, and he will explain how our plunging mechanism works and how we optimize it.
With our half shafts, as asked earlier, what we did to fix the failures we had at competition last year, it's actually to do with half shaft design. We were running a double plunge half shaft with nothing to actually plunge against. So we've left a bit of material in the center of the half shaft so we can control the plunge length at each end of the shaft, and this will give a smoother and more controlled motion and not over travel and pull out. We've also set up the carbon rod in the center, and we've trimmed that to length, so that will actually bottom out before the spring travel, before anything over travels. So it shouldn't pull itself out if there is a failure. We're running 300M steel again, which is a standard automotive steel for axles. We did look into some other other materials like carbon fiber, but it's so stiff and the difficulty in manufacturing it just isn't worth. We don't have time or the expertise at the moment to do it. This half shaft has been optimized to give us the best balance of performance by keeping the amount of rotation, maximizing the use of the rotational energy. So we've adjusted the geometry to the inner and outer diameter and run this through a model, and it should give us theoretically the ability to do a sub 4 seconds or at 100 km/h pass. And that is about it on the half shafts.
I'd like to invite Will and Scott from our Power Electrics team. Hello.
So for this year's electrical design, we've been following on pretty similar from last year. What you see here is an overall diagram of how the electrical system is laid out. So you can see starting from the left, we have the two MRAX motors. These are driven by two Tritium WaveSculptor 200 motor controllers. These are not perfectly matched with the MRAXs, but we already had one WaveSculptor from 2011, and we've proven that they're extremely reliable. We know how to use them, and it was either by one WaveSculptor in 2013 or two new controllers with the two motors in 2013. So we've brought these forward from 2013 into 2014, and then that's covered up with Brad's direct drive system. Moving further along, have the what we call the accumulator. Just as part of the rules, they're very specific with the wording of the electrical system. So when we say accumulator, that means battery box, effectively. And it's actually, going back 30, 40 years, battery boxes were called accumulators. I'm sure it's interesting that it's fallen out of favour, that expression, to say accumulator electric. There's a few people I said. So
So this year for the accumulator or battery box, we're using 96 lithium-ion cobalt cells from EIG, nice little South Korean company. Talk more about those a little bit later on. Monitoring all of those cells is our own battery management system or accumulator management system. We're also, for charging, using the Orion battery management system because of its ability to balance and charge quite fast. As well as that, we also have a DC to DC converter for powering the LV electronics. In past years, we've driven the LV system through a separate lithium-ion little RC battery pack, and that's always been the weakest link with the car, where in previous years the LV system would run out of charge before the main battery pack. Things like the wave sculptors can burn through a lot of power at high RPMs. One wave sculptor can go through 4 amps at 12 volts quite easily. And then moving on to the LV system. One thing we've been working on is integrating the fuse LV distribution, so fuse box, power control into a small compact unit. And this year it's actually now reduced down to an extremely compact unit for all of the LV distribution and cooling controller. So in previous years, controlling fans and pumps for cooling the wave sculptors and the motors has always been a bit of an overlooked, and we tend to just run them at full speed. But it works out that it adds up over time, and that's actually comes back to the LV running out. Having nearly 5 amps of cooling system running burns through a lot of current. And moving along, data acquisition and telemetry. We designed this to be a very modular system. So we have a main data logging system that plugs into, or a main system plugs into the car. It's able to record telemetry from the wave sculptors, the LV power management board. Fall out of my head just then. But then you can connect little sensor modules to it that we've designed ourselves. So you can add sensors to measure tire temperature, shock travel, anything you wish.
Are you going with an electronic diff too?
Yes. That's where this last component comes in. That's what we call the throttle control module. So it connects directly to the pedal box and it measures brake pressure using 2 pressure transducers, and it also measures the actual accelerator position using linear potentiometers. As per the rules for FSAE, we actually have to measure the brakes by using at least 2 sensors and the throttle by using at least 2 sensors. And then there's also on top of that requirements for detecting if this connection's broken or if the signals are noticeably different from each other. So like one sensor measuring the throttle position says throttle goes to 30% and the other one's requesting nearly 100%. So it has to be able to detect that and disable the car.
And what about like differential action between two controllers?
That is done through, actually comes back to the data acquisition system. So this has a steering position sensor amongst it, as well as a gyroscope accelerometer. And this was experimented with last year and used to a limited extent, and we've been doing some testing with it and improving it earlier this year. And I hope to improve it some more.
What was it that failed on last year's car? Because one of the endurance tests you didn't complete.
The first endurance, tripod housing.
Tripod housing,
Yeah.
Mechanical failure.
But you had electrical failure.
In the autocross, we ended up dropping one of our motors, so we had to finish the autocross on one motor. That was an electrical issue that we've managed to find and fixed this year.
The one event you did for your shoulder, or did you feel?
The acceleration event, there was one. Oh, the endurance.
We ran out of
Yeah,
battery.
yeah, main battery ran flat.
Really? Okay. It wasn't light enough, or you didn't charge it fully? Or?
It's both.
So combination of issues that we've been working on this year.
Yeah.
Aerodynamic drag, weight, and battery capacity have all been issues. It's been our main focus this year.
And also the average speed of the track was quite high, much higher than many teams were expecting. So moving on, there's nothing else, just questions with the overall system. Thinking about it?
The BMS that you used, was that off the shelf, or did you have to design that?
I designed the BMS. We're actually using, I should clarify, we're actually using two BMSs. So the charging system uses the Orion BMS, which is off the shelf. That's actually from last year as well. Been using the Orion system since 2011 in one form or another. And they're really good at, I can't think of a particular, good at looking after the batteries. And it's also balances at a very high current rate, which I think it was 250 milliamps, which is quite high. Whereas others down in the tens of milliamps, which means you're just charging for hours.
Because of the rate that it can balance the cells, it actually has a very large heat sink on it, which makes the unit incredibly heavy.
Yeah.
So this year we've decided to remove that BMS from our car because we don't need all that weight while we're running the car. So we've developed our own BMS for the car while we're running, which looks after the cells while they're discharging. And the Orion BMS is actually mounted onto our charging station to take care of the cells when we need to balance them and charge them again.
With the BMS, is it causing much of a voltage drop running it through the BMS, or is it restricting the current through?
Do you mean the BMS actually restricts the output current? We've never implemented that in the past.
Just
even now.
From the tinkering of with bike batteries, found that if you bypass the BMS, then the BMS is actually causing a slight voltage drop of maybe a third of a volt.
If you get like an over voltage BMS cutout or something, have you, or whatever you're talking about? Or?
No, just
is that a current shunt measuring the current coming out of the BMS? So some sort of brick module that you bolt a cable in, cable out, like on the negative pole of the battery.
Yes, you're correct. On the bicycle BMSs, yes, there's a MOSFET in the negative lead of the battery on those, and it works on a current shunt, so it's currently generated as well. And that's causing some voltage drop through the BMS when you're operating the bike.
I follow now. Yeah, the Orion BMS uses a Hall effect sensor that clips over the cable, so there's no shunt with the Orion.
Oh. Have you got only one battery pack, or have you got two switch? Or?
We wanted two, but money is the drawback there, so we only have the one.
So they're pouch cells?
Yes. I'll just, here's in more detail. So EIG, lithium-ion cobalt cells. They're a type of lithium-ion cells rather than lithium polymer. So they have a little bit more stable than the lithium polymer, but as you can see, 3.65 volts. So it's a little bit lower voltage than the lithium polymer cells. This year we've got 355 volt DC nominal system voltage, and that's from the 96 series configuration. What's this side? This here is a picture of one completed cell stack, so we have 4 of these. So this is 24 cells mounted to the circuit board here. So this is actually what holds the whole thing together. And the BMS, each tap connection to the BMS is fused individually by these connections along here. And the BMS for the Orion goes into these connectors, so it's a little bit hard to tell. And the running BMS plugs into, there's 5 headers on the board, and the running BMS just drops in on top. And then that communicates with the other 3 cell stacks in the BMS master over CAN bus.
Two of a few plugs to plug in with the charger. Is that what you're saying?
Yes.
Yeah.
So when we charge the vehicle, we actually remove the accumulator from the vehicle, and we've got 4 plugs to plug in, which goes to our Orion BMS, which monitors each of the 4 cells stacks.
Any other questions with the system so far? No? Very good. Okay, let's just move on to the low voltage system now.
Your worker, you still got, you had your motors and your controller on separate circuits last year. So one cooling system for the controllers, one cooling system for the motors.
Yep.
Still got that same arrangement, or have you got one motor, one controller, one salt, one system, and the other motor controller another system? Or?
This year we've got 1 controller and 1 motor on one system. Yep.
So moving on from the tractor system, been in charge of the general body electronics and the low voltage system. Like we mentioned earlier with the overview, over the past couple of years we've started integrating more and more low voltage control. And that sort of includes centralizing the fuse bus onto a PCB instead of main bus wires into an external fuse box or fuse holder of some sort. And it also doubles up as the tractor system contactor controller. So all the contactors, also the pre-charge circuit during startup, and the bypass contactors once it's fully charged for running state. That's all being integrated into one module. And in further to that, like we mentioned earlier, there hasn't been much development in terms of looking after cooling control and voltage reductions in fans and pumps. Due to the limitation of running a 4-cell low voltage battery pack as the auxiliary, it sort of puts us around the 15.6 to 16 volt range, which is a lot higher than what most of the fans are rated at 12 volts, and that really bumps up the power usage of all the auxiliary components without giving much extra effect in terms of cooling, and just burns more power in general. So we've implemented a couple of voltage regulators switching to just for the fans, and we've got to dynamically control the fan speed on the radiators through testing and temperature sensors to seeing where we need to try and conserve as much power as possible. As we're running the low voltage through a DC-DC converter off the main tractive, we also want to reduce as much auxiliary power as possible and keep it all into the tractive and keep the car running longer.
What is your DC-DC converter?
It's an Emerson. It's sold by Emerson Power or Emerson. It's a 300 volt nominal plus 120 minus 50 isolated, so 15 volts out up to 40 amps. Which is more than we need. Yep. And bundled into that is also typical relay logic to monitor all the safety systems in the car, such as an e-stop vehicle shutdown, temperature sensors, bimetallic switches across all heat generating components. Also monitoring the battery management system, or the accumulator, so the tractor battery management system for what we would call a discharge OK signal, just to say all the cells are OK to discharge, and that would actually, if that signal is not there, we sort of don't allow the car to actually start up at all. Means the batteries aren't, or the BMS isn't happy with something, and it's sort of a dangerous situation. We don't like to run if there's anything wrong with the car, and also a couple of inertia switches and crash switches around the car, just to help monitor every possible thing that can go wrong and shut down the car and let the driver know to get out. Yes. And then all this is now integrated with a microcontroller on board. We sort of run a modular system around the car. We don't have what we would have like a central computer. Every module is somewhere close to where it needs to be, and they all have a micro wheel communicator to CAN bus, and that helps us reduce our low voltage looming and any possible errors in wiring. And main concern is also weight with wires, which really add up when you're running multiple 3-meter pairs to buttons on the dash, etc., etc. And that's just a quick picture of what we've come up with in terms of that module altogether, and that forms the central point of the low voltage body electronics. Any questions?
Thank you, guys.
Nice. Thank you.
All right. I'd like to invite Jamie down now, who's going to accompany me and talk about our chassis this year. I'm not first. Yeah. So this year we've designed a full monocoque. We lost the word. This is different from our last year's chassis design. Last year was a three-quarter monocoque with a steel space frame on the rear. We felt that it was unnecessary to have such a large steel structure on the back end of the chassis, so we decided to create a full tub. So the material we selected to make this is carbon fibre and aluminium honeycomb. The carbon fibre that we've used is an epoxy pre-preg resin system. We chose this because it's specifically designed for honeycomb structures, and due to the nature of the fabric, it makes it a really stiff and strong material for our monocoque skins. We've chosen aluminium honeycomb as the core material over a number of other choices due to its conductivity. One of the rules of the competition state that our chassis must be grounded, and because carbon fibre conducts electricity but not quite enough, we need to add something else to improve the conductivity. So the aluminium honeycomb does a great job of allowing us to earth the chassis properly. It also the aluminium honeycomb bonds a lot better to the carbon fibre skins as opposed to other core materials. And it also creates a shield for our motors, which in the past have disturbed our wireless telemetry. So that's helped us being able to monitor the car while we're out at the track.
This year's car, our hard points are, all of them are carbon fibre hard points, and then we have our one aluminium insert. The reason we did this, carbon to carbon bonding is a lot better than carbon to aluminium bonding, just because aluminium can be a hassle to adhere anything to. It's also reduced weight, so we've got almost 6 kilos of inserts in our chassis, and they're carbon fibre ones. So if they were aluminium, it would be up towards 10 to 12 kilos. Also, better suited thermal properties. So the expansion rate of our carbon fibre inserts is the same as our skins. So there will be less issues if our monocoque goes up to a higher temperature as it does for its curing process.
That's very good.
Okay. Any questions about chassis?
How much is the weight of the chassis in compared to last year?
We don't have an accurate number on last year's chassis, unfortunately. It was weighed a number of times, and we have anything ranging from 30 kilos to 50 kilos. That was in various stages of manufacturing and assembly. But but this year our tub is 27 kilos. So we're quite pleased with how light it is.
Pretty good.
Yep.
I have a silly question, but how do you weigh something that large?
We've got scales that we actually use to weigh the entire car with. So we've been able to sit the chassis on top of those scales. It's not the most accurate way to weigh something, but it's closest to kilogram. So, thank you. Yep, I'll invite down Dynamics. He'll talk about corner assemblies and suspension. Good evening, everyone. My name's Stu, and I'm the Dynamics team leader. Accompanying me, I've got Thomas and Wayne, who are also members of our team. As mentioned earlier on, unfortunately at last year's competition we didn't manage to complete one of the biggest events, which was the endurance event. We targeted a few reasons for this, one of which was the overall mass of the car was a lot larger than we'd planned and designed around, and that had detrimental performance on our battery life. So one of the first steps we did this year with our design process was actually to pull down last year's car into individual components and weigh them and compare them against the values we had for the CAD model. From that, we were able to set some achievable goals for this year, and we basically built our whole design process around that. So for the dynamics section in particular, we were aiming at 46 kilos, which was down from 56 last year. So we set ourselves what we thought was a pretty achievable target. Currently, we look like we're on track to that. We've got the corner assemblies actually machined and assembled at the moment, which account for a large portion of the dynamics package, and they've weighed in at about 10 kilos. So we're doing pretty well as far as that's concerned. We also had some issues last year with driver fatigue in the steering system because it's a manual steering system, no power assist or anything like that, and you're trying to steer quite a sticky race tyre. It definitely takes its toll on the driver through the tight circuits that we negotiate. Part of the way we did this was a revision of our geometry and the whole steering system, and also through reduction of the whole system itself. Another way we differentiate from previous Team Swinburne cars is we're running a 10-inch tyre platform. As mentioned earlier in the drivetrain talk, they made the comment that we're moving to direct drive. This wouldn't have been possible with a 13-inch tyre and the rolling diameter that required. One of the other reasons we moved to the 10-inch tyre is we actually have a lot more tyre compound choices at our disposal, which means that we can achieve far greater lateral grip and coring speed and that kind of thing through simply selecting a different tyre and maintaining it at a good pressure and temperature and having a good level of control over it.
Those can be lighter.
Yeah, they are a little bit lighter, not as much as you might think, but the best thing, I guess, about going to a 10-inch platform is everything is scaled down and you have consequential weight savings as a result. I guess a good hands-on example is a laptop just here. Most of our corner assembly would actually fit on top of that, whereas in previous years, your whole corner assembly would be quite a bit larger, so everything's just been scaled down because it needs to fit within a 10-inch wheel and the constraints you've got. Yep.
On the same sort of note, would it be important that the moment of inertia would be lower as well? When it was a 10-inch?
Yeah, that's definitely the case. And yeah, just dropping weight overall as far as unsprung mass when it comes to the suspension system is quite important because we negotiate through such a tight track. We want the car to actually respond very fast and be a lot more darty, I guess, than other cars in different racing platforms. So it's sort of a bit of a different design challenge there. Now I'll invite Thomas to come up and give us a brief overview of some of the specs and adjustments we have available in our suspension system.
So as you can see here on the list, we've got double unequal length A-arms, so standard setup on any FSAE car. Obviously last year we had a track width of 1120 at the front and 1070 at the rear, which according to this we've reduced by 50 mils at the front and the rear. So as Dougal said, this was to increase our load transfers and make the car more darty. We aimed for a car weight of just on 240 without a driver. So obviously this has a driver in it. The main things with the corner assemblies were our camber, toe, and our caster. So inbuilt into the uprights at the front are 5 degrees of caster, and 1.5 degrees of camber, and static toe half a degree. These are all adjustable on the upright, as we obviously want to perfect our setup through testing. So the A-arms have height adjustment on them through rod ends, and there's also some height adjustment through, camber adjustment through rod ends and like on the steering arms and tow rods at the rear. And we have camber shims on the upright to change the camber. So the steering was also another important thing. With, as Duke said, we had a lot of steering issues last year with strength required. So this year we moved to a longer moment arm on our steering. Went from 65 mils up to 85 mils. I think, 65. Went from 55 to 65 mils on that one. So that would increase our moment arm, allowing us to use less force. And we also reduced our steering angles also, which would mean you have to steer less. So that's about all our setup adjustments.
Any questions at
all?
all?
Yeah, any questions on those?
Do you have linear suspension movement on the suspension or progressive?
I think we have progressive.
We have a slight rising rate.
Yeah, I think that's
running.
You were saying about camber. What was the other thing you said?
Caster.
Caster. What's that?
So camber's obviously we got a whiteboard marker. So
you're going to have to do your best.
Okay, so when you're looking at the tyre from the side, so on the side of the car, you've got your tyre here. Your suspension point here and here, the line between.
Try using a bicycle over there, Tom.
Yeah,
that camber's probably easily described as a bicycle plane syndrome. Basically, you're talking two planes. Yeah. And so, as far as caster is concerned, the caster looking to the front of the vehicle, the caster is the angle formed this angle here, between the contact patch on the ground and directly below the point. Yeah. So it's that angle measured there.
So angle between
front and back of the car.
So it's kind of the camber, but in a different plane of view.
Whereas camber is simply cross car, the inclination of the wheels. So you might have seen some race cars and that kind of thing. Also have the lean on the wheels, that's the camber. Yep.
Just that reason about the trail.
Yeah, so exactly right. Caster and trail are two functions that interrelate. Yeah. And particularly in the suspension design of this vehicle, we spent quite a bit of time optimising that and moving from last year because it has effect on both your steering effort and the self-centering effect of the wheel. If you were to turn through a corner and release your hand from the wheel, having some caster will actually self-center the steering and bring the wheel straight again.
Any other questions in regards to the suspension?
So as part of the steering changes we've gone to this year, there's a certain template required as part of FSAE in the driver cockpit, and you're not allowed to have some components within that space, which poses a challenge with steering geometry because you can't simply have a shaft that goes straight between your steering rack and the position where the driver is at. So last year and the year before, we actually had a beveled gearbox to accommodate for this, which it worked quite well. We never had any failures with it, but there was quite a bit of weight involved in that system. And so one of the things we've done this year is we've actually moved to a universal joint. In previous years before the last two, we had run a universal joint, but we'd had issues with how that was mounted because of some of the loads that were being thrown off by the universal joint. If it's not actually supported properly, it'll deflect, and when your whole steering system starts deflecting, as a driver, it starts to give you some funny feelings and you won't quite turn into a corner the way you'd like to, which isn't what we want from a driver's perspective with our car, because we want it to be as predictable as possible. So there was a great deal of effort spent around the design phase of this system and making it as robust as possible, as well as lightweight to fit in with our goals.
Do you have adjustable shock absorber, damping rates, etc.?
Yep. Yeah, that's all part of our suspension system. I guess I probably should have mentioned it's with the rising rate comment you were making earlier, where the suspension shock absorbers aren't mounted directly to the wheel in the same rate. We've got a push rod and a bell crank that actuates the shock absorbers, and so it's all through that we have control over the suspension. The other change with the steering this year is we've actually changed the steering rack housing. In previous years it's been an all aluminium single piece machined billet, which is quite expensive and complex to machine, whereas this year we've moved away from that and we've actually gone to a carbon composite and aluminium housing.
So there's 2 carbon tubes you can see either side of the aluminium end pieces and the centre. This is allowed for quite simple construction as well as some weight saving, so all fits back into our team goals. Any questions about that at all? Thanks, guys. Okay, pass it over there.
I now have with me Glenn, leader of aerodynamics team, and Lai.
Right. Hi everyone, I'm Glenn and this is Lai, as Andrew said. I'll start off with just going through some things we learned from last year. Last year we had a full aero package, so under tray, front and rear wing. They were quite large and they worked pretty well in terms of providing a lot of downforce, which gave us grip. We got some pretty good feedback from the drivers in terms of the handling. But that led to some issues with endurance. As we mentioned before, we didn't finish one of the endurance races because we ran out of batteries. Two of the main contributing factors, apart from the battery themselves, was weight and drag from the wings. So that was one thing we looked into a lot at the start of the year. So we did some energy calculation tests and other calculations as well. And we basically worked out our drag and weight targets. So we took into account a number of factors: the weight of the car, the weight of the driver, internal efficiencies, the energy that we recover from the regen braking system, and a few other factors like that. And we basically found that we needed to remove some weight. And so we decided to remove the wings because this would allow us to finish endurance and also finish it with speed, so not be crawling around the track. A couple of stats we did find was if we reduce the CD, which is the coefficient of drag, by 0.1, we save 2 cells. Reduce the weight by 5 kilos, we save 1 cell. So though we don't have the same amount of grip when we go around the corner, we save weight not only with the aerodynamic devices themselves, but also less batteries. So I suppose it's a whole approach that worked for us.
You still have the under tray, do you?
It's still the under tray. Yeah.
You still got something else.
Yeah, under tray we can do that fairly lightly, and it's no real extra drag, very minimal. So yeah, and I'll mention that a little bit later on the benefits of, I suppose, keeping that. We also looked at a couple other things that affected drag last year. One was the suspension on the outside, which worked very well for adjustability, but having those components on the outside did create some drag. So we've got a cover over this year's, which adds a couple of benefits as well, but that is one benefit. We also need to do that to meet a couple of the other rules. So that's one thing we looked at. Reducing the overall size of the car. Obviously less area that you're trying to push through the air is going to be beneficial. So we reduced the track width, smaller tyres and smaller cockpit and overall package helped us as well. The main factor was the weight though. This year you're looking at probably about 11 or so megajoules associated to push that weight forward, as opposed to about 3 or so for the drag. So though drag is a reasonable component, the weight was the main thing we're trying to reduce.
Can I just ask again, what difference did it make to the drag coefficient and the weight taking the wheel off?
Quite substantial. The last year's aero
similar to what you showed there.
The weight of last year's aerodynamic package was about 40 kilos, I think, from memory. This year we're looking about 6 or so, less than 10. So we've dropped a lot of weight there. Coefficient drag, we had some estimates, but we didn't have any sort of concrete value for the coefficient of drag, just because of the complexity of it. But it was fairly high. the frontal area of that rear wing was probably 80% of the cockpit or the overall, or the rest of the car. So just removing that rear wing removed a fair bit of drag.
Will you pick up lap times due to increased acceleration as a slower cone without the aero package? You know what I mean? Like,
yeah,
you lose your downforce, but you lose weight, so you can accelerate a little bit faster.
Yeah, obviously you lose that grip going around the corners, which is it would be nice to keep them, but you didn't have that. But yeah, that's a trade-off that you have to make. We prefer to finish endurance than lose a little bit on lap time. And also, I think with less weight, you use less acceleration.
But you should get some back due to increased acceleration.
Because you have the less weight.
Yeah, like your slopes have gone so quicker on the straights, effectively.
Yes, yeah, pretty much. With our track, so it are mostly turns, so it's fairly tight. So the longest straight's 70 meters or that, I think. So most of it is small corners, which is why they have wings. Yeah. Thanks. So we did an. Oh, sorry.
And on this wing, I was wondering, was the wing there to protect some, to basically directly around some kind of exposed beam, or was the wing there for its own purposes? So, in other words, we took the wing away, would you leave any exposed beams, or did you leave them in space?
Do you mean for last year's car?
I guess we're trying to find work out the purpose of the wing. Was it just there to do its thing, or was it sort of trying to direct the air around some horizontal object?
Yep. For the front wing, that does produce downforce, but also pushes the air over the tyres, which it does improve your performance, I suppose, just by pushing the air over the tyres. Not as much as we would have thought, but the main reason is to create downforce, which gives you better cornering speeds.
Right. So in those circumstances, basically you're like fairing the tyres in a sense.
Yes. Yeah, the front wing does aid to guide the air around the tyres.
Right.
Similar to a bearing.
Would you then say, this is just so curious, do you think it's better than not to fair the tyres, or was it some other part of the wing that was causing the problem?
We did an analysis at the start of the year to reduce the size of the front wing in terms of generating downforce, but just to use the wing in order to fair the air around the tyres. We found that the benefits that we gained in drag reduction of having the wing didn't outweigh the added weight and complexity and design of having the wing. So if you were to use the device just to guide the air over the tyres, it's not really worth it. Yeah, so it's easier just to get rid of it completely.
Thank you, that answers the question.
Yeah, at least in our cases, there are some sports car which they do something similar to that, but for our purposes, there was no benefit to having it there.
Right.
This is one of the simulations we've got for the under tray and the car in general. We use ANSYS CFD CFX package. And basically what this image shows is you've got an increased velocity underneath the car. Vanilla equation, if you're familiar with that. So you've got a low pressure zone underneath the car, atmosphere or high pressure zone above the car, which sucks the car onto the ground. As I said, you get some performance benefit because you've got added grip and next to no drag. You're talking maybe 15 newtons at 70 k's or so. So it's minimal. And it also helps put the centre of pressure in the ideal position or a more beneficial position. So you've got your centre of gravity of the car and then your centre of pressure. You want that centre of pressure behind your centre of gravity. If you have it forward of your centre of gravity, the car basically handles like a pickup truck. It becomes very unstable, which you don't want during cornering. Having that centre of pressure behind the centre of gravity makes it much more stable during cornering and also at high speeds too. You don't get the front end sun move around on you, so it stabilises the car, which is another reason why we use the under tray. Now I'll hand you over to Lai. He'll talk a little bit about our side pods and I suppose the benefits of using them.
So back to our team goals, reduce drag and also trying to achieve 760 points at comp. So first with drag, having a radiator just in the middle of the air is quite a big drag spot, creates a lot of drag, so covering that reduces a lot of that. The shape of that also influences the drag on this. By reducing the profile, I've gone for more like a slimmer and a taller inlet profile to reduce the footprint from the inlets. Where the inlet is from the footprint of the front wheel, that turbulent air coming off the front wheel, so try and reduce the amount of turbulent air entering the pod. Also, to increase points, obviously we want to be as efficient as possible, so we want to be as cool as possible. So optimizing the air running through the pod is obviously a benefit. So the inlet size is 65% of the frontal area on the core. That's at the upper reaches of where it should be, but since we're electric, we want to cool a little bit more. With that being slightly smaller, you're allowing the air to diffuse, slow down a little bit as you enter the pod, and as it goes through the radiator, it presents better as it goes back out. By putting the inlet at the high energy position and then the exit at a low energy position, it also draws the air through, and rather than causing a blockage. We also used, you can see in the picture here, a bit of ducting. So the ducting diffuses out slightly from here to here. Upwards it's not. And there's also ducting will be put in on the rear side as well, and this will reduce stagnation because the actual fins are only within this limit, and then this part with the air just gets stuck and can't move through. That's all I've got to say.
As we're trying to increase the mass flow rate through the side pod, increase the cooling efficiency. Cool. Is there any questions regards to that?
So the water will flow through your controller, then your motor, remember?
Yes.
Like from the radio to the motor controller, then to the motor.
Yes. Can't remember what order specifically, but the left motor is in the same loop as the left controller, and they go through the left radiator. And, well, thank you for having us here.
Thanks. That was fantastic. Lots of technical stuff there. So for the inner nerd, it was really great. Hope you do really well this year. We actually did have a little sneaky peek at RMIT's car, and oh, it's good, but yours could be better. We'll see in December how that all pans out. So if you do want a little bit of dirt on RMIT, you can have a look on YouTube and have a look at last month's talk and get the goss on RMIT's secret electrical business. So all good. I just want to remind you about the AGM next month. So I can see some faces around here that could be good for committee members. Not behind, and also that we'll organise something for Christmas, a nice little get together. And there was one other thing as well. Oh yes. There's the new Renew magazine is out at the moment, so go to the newsagent and buy it if you're not already an ATA member and getting it downloaded into your email, or come to our AGM and buy them ultra cheap, as well as back issues as well, and as well as the Sanctuary magazine. So let's make next meeting a big one. Let's get lots of people on the committee, and let's also start organising for an EV Expo in 2015. And let's make it amazing, because I know Team Swinburne will turn up with their winning race car for it. Yeah. Okay. Thank you, everyone.